Density is a great way to relate the mass of a substance to the volume of a substance. Now, mass is how much it kind of like weighs, if you will. Volume is three-dimensional space. Volume is usually listed in milliliters, or what's called a centimeter cubed. That's cm with the 3 in the upper right-hand corner. Mass in chemistry is usually done in grams. And substances will layer themselves according to their density. So for example, if you throw a rock in the water, the rock will almost always sink to the bottom. That's because most rocks are more dense than water. The more dense thing goes to the bottom. On the other hand, if you spill some oil in water, and please don't do that, it's an environmental mess, the oil will float. Oil is less dense than the water, so it's on top. So this superposition is something that's really important, not just in chemistry, but all kinds of fields, to figure out what it is. Going back to the gold and the mercury examples from earlier, gold is more dense than liquid. So you can see that 19.3 is a bigger number than 13.6. The gold would go to the bottom. And the units of density there, grams per centimeter cubed. Grams is mass, centimeters cubed is volume, so it's like mass per volume. Here's a problem you might see when it comes to density. This is like we have a piece of copper. It's a rectangular piece of copper, and the mass is 57.54 grams. And the piece of copper has a length of 9.36 centimeters, a width of 7.23 centimeters, and it's 0.95 millimeters thick, so not very thick, all right? We can actually use this information to calculate the density of copper. And again, density is mass over volume, grams over centimeters cubed. If we're going to do this, all right, the mass part, we've already got the grams, but we're going to need a volume, and a volume in centimeters cubed. And what that means is we've got to get everything in centimeters before we can do any calculations. So let's turn 0.95 millimeters into centimeters. And if you look this up online, or you happen to know, there are 10 millimeters per 1 centimeter. And if you have a millimeter on the top and a millimeter on the bottom, they cancel. So 0.95 divided by 10, 0.095 centimeters. And now that we have the thickness in centimeters, the volume will be length times width times height. And notice here how it's centimeters times centimeters times centimeters. And if you throw this in your calculator, it comes out to be 6.4, and that's 6.4 cubed centimeters, or centimeters cubed. That's the volume of the copper. We can use this then to calculate the density of the copper. Density is mass over volume. So 57.54 grams divided by the volume there, 6.4 centimeters cubed, 9.0 grams per centimeter cubed is the answer and stuff for the density in this problem. Now, if you actually do this in your calculator, you're going to get a different number than 6.4. The calculator will kind of go on and on and on. And I have applied here some significant figures, which is something we'll talk about later, to this problem. So for right now, just take it as a leap of faith that there's a method to the madness and that the density comes out to be 9.0. And later on, I'll talk about how we got those numbers and why I cut them back so much, like in this problem. So here's a question. It says we have a piece of metal. The mass is 33.2 grams, and it's basically placed in 10 milliliters of water. And the question is, what's the identity of the metal? Now, if you look at the little picture on the right-hand side, it starts off at 10 centimeters cubed. And by the way, a milliliter and a centimeter cubed are the same thing. It then goes up to 22.3 centimeters cubed. And the question is, what's the density of the metal? Notice I said density there. If we know the density, we can use the list of possible choices to find the identity of it. So on this problem, this makes sense to first find the density and then find the identity. And this problem uses what's called the Archimedes Principle to figure it out. And what Archimedes' principle is all about is basically if you add a rock to water, the displacement of the water is equal to the displacement of the solid, i.e. the volume. So we're going to use the difference in volumes there to figure out what the volume of the metal is. So mathematically, this is not really a hard problem. Mass of the metal, 33.2. Volume of the metal would be 22.3 minus 10, or 12.3. So in this problem, the density comes out to be 2.70 grams per centimeter cubed. And again, you get that by mass divided by volume. And you want to use the displacement system. And Archimedes is this person that supposedly was in the bathtub, and he sat in it, and he realized the water went up as he sat down. And he's like, oh yeah, okay, the volume displaced is equal to my volume. And he used it for metal. And supposedly it helped them to solve this problem they were having with fake gold versus real gold, which is kind of cool. So the number that you calculate, 2.7, is certainly closest up here to AL, answer E, so that's where this one comes from. The densities of the elements are all over the place. They generally on the periodic table tend to bulge around the middle part. The osmium and iridium, you can see, are bigger than all the other ones. There are some distinctions. We'll talk more about them and stuff, but all substances arguably have a density. Some of them are very similar to each other, but some of them are quite different. So a lot of times identifying an unknown is as simple as just finding the density of the item. Density is an intensive property, which means it doesn't mean how much of it you have. So you can have a little bit of brick or a lot of brick. The density should be the same. The relationship between the mass and the volume will not change depending on the quantity. And this is a cool distinction. Things like boiling points and melting points also don't matter as to the quantity. You can have a little bit or a lot, should be the same boiling point. Now that's quite different from extensive. Extensive means that you do need to know how much you have. So mass, for example, is extensive. 5 grams is a lot different than 500 grams. So you'd have to know like how much mass you have. But density, as long as you have just a little bit of it, you're good to go. It'll work for the bulk, which is kind of cool. Here's a problem. Mercury, quicksilver, has a density of 13.6 grams per centimeter cubed. And it says, what's the mass of 95 milliliters of mercury? What's the mass in grams and in pounds? And this is a typical kind of problem that involves density. And if you're going to do problems like this, and like most problems in chemistry, you're going to use this process called dimensional analysis. And dimensional analysis, which is sometimes called factor label, just means that you're starting with some kind of unit and you're converting it to a new kind of unit. And along the way, you need a conversion factor. You need to know what you're starting with, and you need to know what you're ending with. So on this problem, you are starting with 95 milliliters of volume, and you have certain types of units here. You have a density, all right, and you want a unit in grams, and you also want a unit in pounds. So notice here what I'm doing. I'm figuring out what my starting unit is, and I'm also figuring out some conversion factors to get to the units we want. We want grams and we want pounds. 1 centimeter cubed is the same as 1 milliliter. And I kind of babbled about this earlier with the problem on the other thing, but a centimeter cube is length, width, and height all equal to a centimeter. And that literally is what a milliliter is. It's a milliliter of volume. So you can interchange milliliters and centimeters cubed all the time. So up there it says 95 milliliters. You could call that 95 centimeters cubed, and that's totally cool. Centimeters cubed are usually used for solids, while milliliters are usually used for liquids, but again, you can interchange them if you want to. It's not a problem. So in this problem, let's call it 95 centimeters cubed. Let's skip right to it, because a milliliter and centimeter cubed do the same thing. And then if you multiply it by the density, notice that your starting unit, 95 centimeters cubed, the centimeters cubed they cancel out. Centimeters cubed over centimeters cubed would be like x over x in math. It's just equal to 1. So those units cancel out. And grams is the only unit left forward. So 95 times 13.6 is 1.3 times 10 to the 3, or 1,300 grams. And that's the answer for mass in grams. Before we do the pounds, notice we started with 95 centimeters cubed, 95 milliliters. We used a conversion factor, and we canceled out the starting unit, and we ended up with the desired unit. And that's really what dimensional analysis or factor label is. You're starting with something, you're using a conversion factor to cancel it and get to your desired unit, and you're good to go. Sometimes there might be more than one conversion factor, but that's really all this comes down to. Now, the second part, we need to try to figure out the mass in pounds, and you're going to need a conversion factor for that. Now, if you happen to know the conversion factor, cool. If you don't, it's about 454 grams per 1 pound. So now what I would do is you're starting with grams, you want to cancel the grams, and you want to have pounds. So in this next part here, then, you'll put the grams on the bottom and pounds on the top. The 454 goes with the grams, so that goes on the bottom. Grams divided by grams cancels out. You've got just pounds. The abbreviation for pound is LB. In your calculator, you'd go 1.3 times 10 to the third divided by 454. No reason to multiply by 1 and then divide by 454. That's too much work. So 1.3 times 10 to the third divided by 454, 2.9 pounds. Again, I'm cutting some of the numbers off from what you're getting in the calculator because of significant figures, and we'll talk about that here in a little bit. Volume is really interesting, and again, there's a couple different ways to do it. If you've purchased soft drinks in the store or something like that, a lot of times it's in liters or milliliters, all right, which is totally fine. But solids, a lot of times, will use length times width times height units. So, for example, a centimeter cubed, we've seen a lot already. And the important part, more important than anything, I would argue, is that a centimeter cubed and a milliliter are equal to each other. Now, there are 1,000 milliliters per liter, so that would mean 1,000 centimeters cubed in a liter as well. Sometimes, especially in science and physics, they'll use meters cubed, no problem. You can convert meters cubed into centimeters cubed and stuff like that. We'll talk about those in a little bit. But just realize that's what it is. It's literally three-dimensional space, all right? But the important part for us in chemistry is that a milliliter and a centimeter cubed, same thing. Temperature is another important conversion factor that can be used for boiling points, melting points, and a whole bunch of stuff. There are 3 main temperature scales that we're going to use in chemistry: Fahrenheit, Celsius, and Kelvin. And they're all named after the people that kind of developed them. Now, what we're going to do most of the time in chemistry is we will make measurements in the lab in Celsius. And for calculations, we'll convert the Celsius temperatures into Kelvin temperatures, and vice versa. On the other hand, we live in the US of A, in good old Oregon. And Oregon, if you watch or listen to any of the news channels, they're always recording temperatures in Fahrenheit. So you must know how to make conversions to your regular life. You must know how to go from Celsius and Kelvin to Fahrenheit and vice versa. We won't use Fahrenheit very much in this class. It's not a very useful unit for science, as we'll see. But Celsius and Kelvin are going to be the 2 main ones, but we are going to know how to go back and forth and stuff like that. There's a relationship between the 3 temperature scales and the freezing points and boiling points of water. So if you grew up in that good old Gresham, Oregon, like me, well, water freezes at 32 Fahrenheit, water boils at 212 Fahrenheit, and the difference between them 180 and stuff like that, and that's fine. However, Celsius and Kelvin have a lot of advantages. Celsius, water freezes at 0 Celsius, and it boils at 100 Celsius. And notice that the difference between those is 100 degrees. 100 minus 0 is 100, all right? Kelvin, it's a little weird at first, but there's 273.15 where water freezes and 373.15 where water boils. And the difference between those is also 100 degrees. So because the difference is the same, a degree Kelvin change is the same as a degree Celsius change. And that's going to be so cool to us later on. I can't even begin to tell you. Fahrenheit, because it's 180 degrees difference, you're going to have to make some weird kind of conversions and stuff. So scientists will usually, like I said, record temperatures in the lab in Celsius. And for calculations, we're going to see there's uses why Kelvin is better for calculations. So easy to convert one to the other. But Fahrenheit, it's going to be a lot different, so no problem. So try to use Celsius and Kelvin in the lab. In your real world, you can use whatever you want, all right? But in this world and stuff, use Celsius and Kelvin. So here's just examples: 100 Fahrenheit, 38 degrees Celsius, 311 Kelvin. Water, 32 Fahrenheit would be 0 Celsius, 273 Kelvin. A couple things about Kelvin. If you haven't seen this before, Kelvin for our uses in chemistry will never be a negative number or a negative or even 0. All right, Kelvin is always a positive number. Kelvin scale represents the place at 0 Kelvin where all matter stops moving. And in theory, that should be impossible. But there are some experimental kind of theoretical things going out there where maybe you can have negative Kelvin. And that's really cool, just like I like talking about science fiction, but that's not appropriate here. So for Chem 221 through Chem 223, no negative Kelvin temperatures. Also, officially, there's no degree Kelvin. If you look at the scales down here, like it's degrees Fahrenheit and it's degrees Celsius, but Kelvin doesn't have that little symbol. So Kelvins aren't supposed to have degrees. And a lot of times in astronomy and in photography, they'll use these degree Kelvin symbols, and it makes my chemist's hairs in the back of my neck stick up, but they're not supposed to do that. So try to not use degree Kelvin if you can help it. Here's an example. Again, my jokes. This is Foxtrot. It says recipe says to bake the cookies 350 degree oven for 14 minutes. And sorry, I'm cracking myself up. And I've read this comic several times anyway. Does it mean degrees Fahrenheit or degrees Celsius or degrees Kelvin? And then the brother comes in and goes, maybe you should just rotate the oven just shy of a full circle because a circle is 360 degrees. And this brother goes, don't be ridiculous and stuff. Anyway, it shows the importance of knowing what type of scale you've got, all right? Because 350 Fahrenheit is quite a bit different than 350 Celsius or 350 Kelvin, absolutely. So knowing what type of unit is important. Now, probably in this one, because again, this is a US of A comic, it was probably 350 Fahrenheit, but on the real world, you should be really careful. And of course, if you have a recipe from Europe where they use Celsius, it might be in Celsius, so just be careful. If you're going to convert Kelvin to Celsius, Celsius to Kelvin, it's pretty chill. You want to use that 273.15. And again, remember that Kelvin temperatures will never be negative. So if you end up with a negative Kelvin temperature answer, and this is and you're in a chemistry class with me, then probably the calculation is wrong. But Celsius can be negative. So to the temperature in Celsius, you want to add 273.15 to get the Kelvin. And of course, if you have Kelvin and you want to go to Celsius, you would subtract 273.15 from the Kelvin temperature to get the Celsius temperature. So body temperature, about 37 degrees Celsius. Wonder what that number is in Kelvin, Dr. Russell. Let's figure it out. Celsius plus 273 is how you do it, 310. Now, notice I didn't put the 0.15, and I added a little dot right there. Both of those are intentional, again, based on significant figures. And we're going to talk about that here in a little bit, I promise. But we're not there yet. So for right now, just bear with me. 37 turned into Kelvin, 310 with a dot Kelvin temperature. Liquid nitrogen, very, very cold. Terminator 2 froze the Terminator down, stuff. Anyway, temperature of liquid nitrogen, minus 196 degrees Celsius. Remember, Celsius can be negative, but Kelvin won't. So if you wanted to turn that into Kelvin, you'd add 273 to it. 77 Kelvin would be the liquid nitrogen temperature. if you have to use Fahrenheit. Totally legit. It's kind of a drag, but anyway, what I would do is if you're starting with Celsius, you want to turn to Fahrenheit, you multiply the Celsius temperature by 9/5 or 1.8, and you add 32. Some textbooks you'll see the 1.8, some textbooks you'll see the 9/5. It's the same thing. Whatever you want to do is fine. 1.8 times the Celsius temperature plus 32 is it. So, liquid helium, 4.2 Kelvin. If you wanted to turn this into Fahrenheit, what I would do is I would go Kelvin to Celsius first, and then Celsius to Fahrenheit next. Now, Fahrenheit can be positive and negative just like Celsius, but again, Kelvin will not be. So, Kelvin minus 273.15, you get negative 269.0 degrees Celsius. And yes, I am including that 0.0 for a reason. Yes, it has to do with significant figures. We'll talk about that here in a little bit. Anyway, for right now, knowing that's the Sigfig answer, if you wanted to convert that Celsius to Kelvin, you would throw that into the 9/5 times the Celsius plus 32. And when you get this out, negative 452.1 degrees Fahrenheit is the temperature of liquid helium. And that is really, really cold. Brr. But anyway, again, Celsius to Kelvin, Kelvin to Celsius a lot, once in a while Fahrenheit. So here's temperatures that you can read, that you can actually experience on the Earth. 29 Celsius, 45 Fahrenheit, 256 Kelvin. Let's put them in order of increasing temperature, all right? What I would do in a problem like this is use Celsius as the halfway. So I would turn Kelvin to Celsius, and I would turn Fahrenheit to Celsius and see which one it is. So in this particular one then, 256 Kelvin, you would subtract 273.15 from it to get the value. That's going to be something that's pretty cold. It's going to be a negative number. So 256 Kelvin will definitely be colder than 29 degrees Celsius. Now, Fahrenheit, 45 Fahrenheit, if you wanted to turn it in, you would first subtract 32 and then divide by 1.8 or 9/5. And you'll see that that value is also smaller than the 29 Celsius. So of those, the 256 is smallest. It's going to give you a negative Celsius. 45 Fahrenheit won't give you a negative, but it will be a smaller number than 29. So 29 would be the largest. Again, in your studies, make sure you know how to go Kelvin to Celsius, Celsius to Kelvin, and just know that there's a way to go from Celsius to Fahrenheit if you need to. Now, when it comes to measurement, all right, there are qualitative measurements, which is like what kind of color it is and stuff, or is it a solid, is it a liquid? And those are really cool kind of things, all right? Qualitative analysis is actually an important part of chemistry, and we're going to do a whole series of labs at the end of Chem 223 if we have face-to-face labs, where we'll use qualitative observations to figure out what's in an unknown compound, stuff like that. But a lot of chemistry is quantitative, which means how much of something and what type of that you have. So if you're going to do quantitative measurements, which is a lot of chemistry, that's where the metric system comes in. But you can have different bases, and this is where the metric system is so cool. So for example, the base unit of length is the meter. The base unit of mass is gram or kilogram, depending on what you're talking about. Base unit of time is seconds. You can apply the metric system to all of these. So let's use metric for the length part here. You can have a kilometer, which is 1,000 meters. You can also have a centimeter, which is 0.01 meters. You can apply all the different metric prefixes to these, which is really cool. And you can do the same for mass. You can do the same for time. It's really, really cool. However, there's a problem sometimes when you're taking measurements. You have to know about the accuracy and the precision of the measurements you're taking. And let's use this cheesy example here with a dartboard at a bar. And let's say that you have a couple, you're there to see your friends and you decide to play darts and you're really good at darts and man, you throw them and oh wow, all three of the darts right in the middle. Well, the blue circle represents the accuracy of the measurement. and you were super accurate. All right, they were all right there. And also, because all three measurements were really close to each other, or all three darts were thrown at the same part of the board, you have a high level of precision. So accuracy and precision are both important in chemistry. Hopefully, you have, at the very least, good precision. And of course, if you're worth your weight and stuff, you should be able to make accurate measurements as well. However, same thing, you've had now a root beer or two, over 21 and stuff. Anyway, and you throw the darts again, but your root beer is just interacting so much with your body, you're too sugared out or whatever, that you throw the darts and, now they're not really close to that blue dot, but you threw them all in the consistent manner, and they all ended up in the same place. So I would call this a series of measurements that were very precise, like they all ended up about the same value, but they weren't very accurate. You wanted to be by the blue dot, and of course they weren't even close to that. So this is an example of a series of measurements which has high precision, but not very good accuracy. So your friends say, hey, don't worry about it. Here, have another root beer, and again, I'm coughing because maybe you have something other than root beer. Anyway, my silly jokes. Anyway, you have another couple of your root beers and you decide to try the darts once again. But this time you're pretty well jolted on caffeine, sugar, whatever the active ingredient is. And this time, you throw the darts and, man, you can't hit the side of a barn. The darts are all over the place. They're not close together. You don't have good precision. The darts are all over the place. They weren't like tight together like they were before. And they're not even close to the blue dot. You don't have good accuracy either. Now, I bring up this very silly example because this is what measurements are like in chemistry. You have to know, or you have to have an idea anyway, as to how accurate they are and how precise they are. And you should be, if you don't know anything about the chemical system, you hopefully will at the very least be able to have high precision, like you're paying attention, you're making good measurements that are repeatable. But even if they are close to each other and repeatable, you should be careful because you don't really know about the accuracy unless you have other methods to confirm what you think you know. Accuracy just refers to the proximity of the measurements to the true value, all right? So if you wanted a length of 3.5 meters and you measured 3.49, that's going to be pretty high. You can actually determine how accurate you are through what's called a percent error calculation, and we'll do some of this in lab if we have lab. Precision, on the other hand, refers to the proximity or reproducibility of several measurements to each other. So if your three darts are really close to each other, that would be like making three measurements that are very consistent. They have very approximately the same values. And we can figure out how precise measurements are by using something called parts per thousand, which is a variation of what's called an average deviation. We will use percent error and parts per thousand in lab to tell how accurate and precise our measurements are. This is the thing, how to find experimental error or percent error, and I'm not going to go through a lot of details, but I want to just show here what some of the things are. In an average deviation, you'll take the difference between the average of your numbers and the individuals. Standard deviation is used a lot of times in math, although we don't use it in chemistry very much, and a parts per thousand is the average deviation divided by the average times 1,000 stuff, no big deal. This will make more sense in lab when we do it. But a parts per thousand, that's how we measure the precision, how close the measurements are to each other. Smaller parts per thousand means more precise, higher parts per thousand means less precise. Percent error, you do need to know the accepted value, maybe from an experimental paper that was published or some other important group. It's the difference between your value and the accepted value divided by the accepted value times 100%. And again, the smaller the percent error, the better your measurement, your calculation was. This is an example. You can go through it later if you'd like to. These are 4 boiling point measurements. They found the average of those 4 measurements. They then found the deviation, which is the difference between the average and the boiling point measurement. So for example, the first one, you would go 11.23 minus 11.19 for 0.04. For the second one, it's an absolute value, which means make it positive. So 11.09 minus 11.19 0.19 comes out to be negative 0.10, but it's listed as positive. Deviations are always absolute value, i.e. make them positive. Finally, if you take the average of all the deviations, you get what's called the average deviation. So if you took 0.04 plus 0.10 plus 0.08 plus 0.03 and hit enter, that would be some number, and you would divide it by 4, the number of deviations, number of trials, to get the average deviation. So the average deviation is 0.06. You could write that as 11.19 plus or minus 0.06 if you wanted. Parts per thousand, average deviation divided by average times 1,000. 0.06 divided by 11.19 times 1,000 is 5 parts per thousand, so they're pretty precise. And if the accepted value was 11.25, the percent error would be, again, the difference between them divided by the accepted value times 100. Percent error sometimes is absolute value, which means always positive. I put it here in the negative version just so you know what it's like and stuff. You should be good to go. We'll do these things in lab. So if right now you're like, blah, 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 then don't worry about it because we're going to do it in lab. And it makes a lot more sense, in my opinion. Now, I've been talking about significant figures. We've been cutting things off, so it's time to talk about what significant figures are all about. In a measurement, you want to, of course, have the highest precision, highest accuracy possible. But a question comes around in all measurements. For example, if you have water in a graduated cylinder, what is that number? What is that measurement? Now, first of all, notice how there's a little bit of a curve. That curve on the water is called a meniscus, and people will usually try to measure from the bottom of the meniscus. And if you look on the left side, 15 is the big one, 16, 17, 18, 19, 20. So I think we would all agree that the bottom of that curved meniscus is between 17 and 18. But how many digits do we call it? Do we call it just 17? Do we round up to 18? Do we call it 17.5? Do we call it 17.4876? I mean, what do you call it, right? And the important thing here, all measurements, whether they're made by a computer or a human, have uncertainty. There's going to be some known digits. So for example, 17, that thing is definitely known, but there's also going to be a doubtful digit. What's that next value listed? And this is where significant figures really pops in. It tries to make all measurements made by scientists standardized. So it will have consistent measurements. We won't go crazy and stuff. The calculator is going to give you lots and lots of numbers, but not all of them are significant. And this is probably the most important of all of the topics we've talked about in this chapter so far. Significant figures is the cornerstone of all experimental science. And chemistry is just chock full of experimental science. So you've got to know your Sigfig system. As the teacher, I take off more points for Sigfig errors than anything else. So if you spend the time in this chapter learning significant figures, you're going to be good throughout the whole class. So I can't tell you enough how important this section is. So let's look at the rules for what scientists would use to make this measurement. In a number, you're always going to have some known values, which are people feel confident, but there's also going to be one digit which is estimated. And they call this estimated digit the doubtful digit. And if you've ever seen a journal article, it'll say some number plus or minus some other number. The plus or minus is usually the doubtful digit. It's the one that's uncertain. And so if you looked at a number, maybe you'd call it 17.4. But if I looked at it, it might be 17.5. Or if someone else looked at it, maybe they call it 17.3. There's a plus or minus in that last number, and that's what the doubtful digit is all about. So every number is going to have some known values plus one doubtful digit, and the doubtful digit is just the last number. The total number of digits is called the number of significant figures, and significant figures is obviously abbreviated Sigfigs because that's a lot of syllables and stuff, but that's important too. So we need to know in any number how many significant figures there are and which one is the doubtful digit. Here's some examples. 65.07. Okay, the last digit is the doubtful. So the 7 here is the doubtful digit. And 65.07 has 4 significant figures. The 6, the 5, the 0, and the 7. Those are all significant. Even the doubtful digit counts as a sig fig. So 4 sig figs, 7 is the doubtful digit. The 7 is the hundredths position, if you remember from math. Here's another number. 54.70318 has 7 digits, 7 sig figs, all right? And the 8, that last position, that's the doubtful digit. So it goes tenths, hundredths, thousandths, 10,000ths. That's the 100,000ths position. That's the doubtful digit. But all those numbers are the number of sig figs. And you're probably seeing here that the more sig figs you have, it's going to be better as a chemist, because we're so obsessed with these kind of things. So just get ready. The zeros are troublesome, though, because sometimes zeros count in a sig fig and sometimes they don't. If the 0 is in the middle of non-zeros, it counts. So like earlier we saw a number with a 0 in the middle, and that counted as a sig fig. So 69.08 would be 4 sig figs. The 8 is the doubtful digit. If the zeros, though, are at the beginning, then they don't usually count, as they're not significant. They're called placeholders. So like 0.0089, we want to know where the 8 and the 9 is on the number line, all right? This number, 0.0089, is not 89, and it's not 8.9. It's 0.0089. So that number has only 2 significant figures. If you know about scientific notation, you could write 0.0089 as 8.9 times 10 to the minus 3. Notice that all of those zeros go away in scientific notation. That's another way to tell there's only 2 sig figs in that number, and the 9 is the doubtful digit. At the end of the number and after a decimal point, those zeros count. So for example, 2.50, 3 sig figs. The 0 is the doubtful digit. 25.00, the last 0 is the doubtful digit. That's 4 sig figs. I like to think about this as chemists are lazy. We won't include those zeros unless there's a meaning, because we could write it 2.5 and 25 and that would be fine. But we decided to include it. That's because those are significant figures. So the 0 after the decimal and after a non-zero, those count. If the zeros, though, are before a decimal and after a non-zero number, then you have to be a little careful, all right? Most of the time, they're only significant if there's a decimal placeholder or a period. So let's look at these two numbers, 1500 with no dot, 1500 with a dot. 1500 with no dot, the first one, we would assume has only 2 sig figs. We could write that 1.5 times 10 to the third, and the zeros go away. On the other hand, 1500 with a dot means that the zeros are significant. So 1500 with a dot would be 4 sig figs, and we would write that 1.500 times 10 to the third. I used a dot earlier with the Kelvin temperature. I think it was 310 Kelvin or whatever. I wanted that 0 to be significant, so I put a dot next to it. Those dots are important in chemistry. They are not accidents, all right? They will be meaningful. So 1500 without a dot, 2 sig figs. 1500 with a dot, 4 sig figs. If you had a number 1500 that you wanted to have 3 sig figs, I would write it in scientific notation, 1.50 times 10 to the third. Finally, there are some definitions or exact conversions which have what's considered to be infinite sig figs. So, for example, 60 seconds per 1 minute, that is never going to change. You're always going to have 60 seconds in a minute. All right, you're never going to have anything different. So 60 and 1 both look like 1 sig fig numbers. We don't want to have those limit our sig figs. So those are considered definitions and they don't affect your sig figs. Also, 10 millimeters meters per 1 centimeter. Those look like 1 sig fig numbers, but they aren't. They're exact conversions. There'll always be that case. 1,000 meters in a kilometer, 1,000 milligrams in a gram. Those would be other types of definitions where we don't worry about the sig figs. Density, on the other hand, is something that you need to measure mass and volume. Those are not infinite. Those would be significant figure kind of values, and we'll talk about that later. Very important to practice, all right? In the textbook and in the companion, there are practice sample quizzes, examples, and stuff like that. I highly recommend you go through these and stuff to learn them. Sig figs, like I said, super important, and you've got to know how many sig figs there are and when they count and stuff like that. The zeros are the troublesome ones. The other ones are pretty chill. Here's some numbers. Let's see here, how many of them do they have the same number of significant figures? All right, so the top one, 1,000 with a dot. Notice the dot. That means those zeros count, 4 sig figs. Second one, 9.730, 0 at the end and also past the decimal. That definitely counts. That's the chemists are lazy thing. We wouldn't write that 0 unless there was a meaning for it. So that one counts, or has 4 sig figs. The next one, 0.004270. So the initial zeros are just placeholders. But the last ones, the 0 at the end, we wouldn't write that unless we needed it. You could write that number as 4.270 times 10 to the minus third. That is 4 sig figs. So those don't count in terms of sig figs, but those last 4 do, 4 sig figs. And this last one, zeros at the end, no dot, 4 non-zero values, 4 sig figs, true. They all have the same number of significant figures. They all have 4 sig figs. Scientific notation is something that I'm hoping you've heard of before, but if you haven't, it's a really easy thing to do. Chemistry has numbers that are super big when it comes to like number of water molecules in a teaspoon or something like that. But we also have numbers that are super small when it comes to like the distance between the oxygen and hydrogen atoms in the water molecule. And if you use scientific notation, you can easily express these numbers. Do not make your instructor count your zeros. All right, I will be totally mad and stuff like that because you don't have to. If the number is like larger than 1,000 or smaller than 0.001, you had better use scientific notation. So let's look at some examples of how this works. Scientific notation is always the number between 1 and 10 times 10 raised to a power. And 215, if you want to write that in scientific notation, as a number between 1 and 10, it would be 2.15 times 10. If you move the decimal to the left, you make it a positive exponent. So we moved it 2 to the left. That's where the 10 to the second part comes in. So 215 would be 2.15 times 10 to the second. If you see a number with a negative exponent, that doesn't mean it's a negative number. It just means it's a really small number. So 1.56 times 10 to the minus 8th, the negative 8 means that we had to move that over quite a few zeros, all right? So if you start with 1.56 and you go 1, 2, 3, 4, 5, 6, 7, 8, 8 decimals to the left, or you'd have 7 zeros and the 1 now is a number, that's how you would do this kind of thing. All right. Scientific notation is pretty easy to use, but it's super important. And if you have a modern calculator, you must know how to go from regular format to scientific notation and back and forth, because we're going to use numbers that are super big and super small. So spend some time finding on your calculator how to convert to scientific notation and also how to go from scientific notation back to the regular. The calculators usually have an EE button for powers of 10, but there's also some way, like a mode usually, and it'll say science or normal or something like that. If you can't figure out how your calculator can do this, let me know. Most of the science calculators will have this on there, but if you don't see it, please contact me. Calculators, when you do a calculation, will create just incredible numbers of digits sometimes. But in chemistry, we only want to use the Sigfigs in our answer. And we're going to have to round these large calculator numbers off to something that's manageable. And we've already seen that in a lot of the examples in this chapter. I rounded up some of the things and stuff because of these Sigfig rules. So let's look at how you round numbers with significant figures, especially when it comes to problems with chemistry. In chemistry, most of the time we're going to be using Sigfigs with problems involving multiplying and dividing. And the answer cannot have more significant figures than the original numbers. So let's say that you take your car out and you drive 278 miles. And you figure out that you use 11.70 gallons of gas, assuming it's gas powered, to make this happen. All right. Well, mathematically, you throw this in your calculator, it comes out to be 23.76068, blah, blah, blah. I get bored after writing too many numbers. When it comes to to significant figures, you can't express the number in any more than the smallest sig fig. So if you look at the numbers that went into this calculation, 278, 3 sig figs, and 11.70, 4 sig figs, all right? The final answer has to have the smaller number of sig figs. So because this one had only 3, our answer is going to only have 3 sig figs as well. So 23.76068 becomes 23.8. Notice here that we rounded up the 7 to 8. If the first number you drop is between 5 and 9, you round up. So 23.76 to 3 sig figs, 23.8. So when you multiply and divide, the smaller number of significant figures is what you use in the final answer. This is why chemists are always fighting for significant figures, because you want them as you calculate things and stuff like that. So multiplying and dividing, not too bad. The same process would have been worked if we would have multiplied those numbers together. Adding and subtracting is a little bit different, and this is where the doubtful digit pops in, and the answer has to be rounded to the larger doubtful digit. So here's an example of taking 3.18 liters, and we're adding 0.01315 liters to it, okay? Now, mathematically, it comes out to be 3.19315, all right? No big deal, not hard math to do. However, in the 3.18, the doubtful digit was the 8, or the hundredths spot. And we really don't know what those other numbers are to the right of it. All right, maybe they're all zeros, but that's not very likely. They could be something else. Now, the second measurement, which was smaller, we knew more digits. It went out to the 100,000th of a number, all right? And that's really cool. But when you're adding them together, we really don't have any confidence in those 3 numbers because we don't know what went into them. So what chemists do is they cut it off at the largest doubtful digit. 3.18 stops at the 8, and that's where this number stops as well. So 3.18 plus that 0.01 blah, blah, blah becomes 3.19 liters. We're cutting it off at the larger doubtful digit. 3.19, we're cutting off the 315, and we're making this just 3.19. So adding and subtracting is a little strange. You want to use the larger doubtful digit to cut off your answers for them. So even though in that second number, 0.01315, we had all kinds of significant figures, we're going to cut it off at the hundredth spot to 3.19. Work a little bit on adding and subtracting in sig figs. Sometimes people get a little stuck on it. And it's not hard, you just need a little practice. Rounding up, which I already mentioned earlier, is something you may have to do. If the first digit that you're going to remove is between 0 and 4, you just drop it and leave the number alone. But like we saw in the multiplying dividing, if the first digit you drop is between 5 and 9, round it up. So 2.4271 would become 2.4 when you round it to 2 sig figs, because the first digit you drop is the 2. 2 is between 0 and 4, so you just leave the 2.4 alone. On the other hand, 2.5816 becomes 4.6 if you're going to round it. You're going to cut it off after the 5. The first digit that you drop is an 8. That's between 5 and 9. So 4.5 becomes 4.6. Now the textbook says something in there about even rounding with a 5. Don't just ignore that. That's just silly. All right, I don't know what they're talking about. You just want to use the simple way and stuff. 0 to 4, leave it alone. 5 to 9, round up. Pretty chill. Let's round this number up to 3 significant figures. Now, first we have to see where the Sigfigs start, all right? And remember that zeros at the beginning usually don't count in terms of Sigfigs. So the first digit to count is this 3 right there. So 3 Sigfigs, 0.00303, that would be 3 Sigfigs. And then we'll cut this part off, and it might be tempting to say, oh yeah, 0.00303, but the first number dropped is 5, and 5 is between 5 and 9. So 0.00303, we're going to round up by 1 unit. That's going to be 0.00304. 5 was the first digit drop. It's between 5 and 9, so 0.00303 becomes 0.00304. Mass percentages are something we'll talk about. Mass percentages in 100 grams, then the percentages represent grams of the compound. So if you have 30% lead and 70% oxygen, then in 100 grams you would have 30 grams of lead and 70 grams of oxygen, which isn't too surprising. You can also use like 1 gram. So in 1 gram, you'd have 0.30 grams of lead and 0.70 grams of oxygen. That's fine too. A lot of times I'll talk in terms of 100 grams because people tend to see it pretty easily, but you're welcome to use just 1 gram or a billion grams, whatever you want, in order to figure it out. Here's an example with a penicillin compound. This penicillin F compound is 53.829% carbon. So again, what that means is that in 100 grams of penicillin F, you would have 53.829 grams of carbon. And it says how much carbon is in 75 grams of penicillin F. So, like we said, that percentage means that in 100 grams of penicillin F, 53.829 grams. So we're going to take the 75 grams of penicillin F, multiply it by 53.829 divided by 100, or if you'd rather, 75 times 0.53829. Either way is fine. But the idea here is that you want the penicillin F to cancel. In the way I did it here, I had 100 grams penicillin F on the bottom, 53.829 grams carbon on the top. I'll multiply those two together. I get a number with a whole bunch of units, but because of 75, 2 sig figs, multiplying it by a number with 5 sig figs, I need to cut this off at 2 sig figs. And after the 0, the first digit to be dropped is 3. That's between 0 and 4, so I don't round up. 40 with a dot grams carbon, 40 dot grams would be the answer. And again, the dot just means that 0 is significant. If you just wrote 40 without a dot, it would look like a 1 sig fig number. And you don't do that in chemistry. Always put the dot there if it's a 0 that's significant. Volume percentages are occasionally seen, like you could have 10% by volume ethanol in water, something like that. We won't see them in our class, but it is possible to have a volume percentage. If you see a percentage in our classes, Chem 221 through Chem 223, they will be mass percentages. So it just means use grams, all right? Don't use milliliters or centimeters cubed, stuff like that. Okay, that's actually the end of Chapter 1's notes, and that's really cool. I'm so glad you stuck with me. Some more help on Chapter 1 can be found in these little pieces right here. There is a study guide for each chapter, and the study guide is just a bulleted list of the important parts from the chapter, and you can go through that to make sure you're good to go. A concept guide also follows these. Concept guides are worked problems using some of the concepts concepts we've talked about in this section. So I would definitely look through the concept guide. It'll give you some ideas on how to use Sigfigs and how to do temperature conversions and stuff like that. Now, most of the chapters have just one concept guide, but there is a concept guide. I called it Chapter Guide 0 for math, and it's just an overview of some of the math skills. And if you're having questions on percentages or adding or multiplying or any of this kind, powers of 10, definitely check this out. It's not required, but it's a cool thing to kind of get you up to speed. Also, I'm not going to show them in this video, but there is a section of some important equations which follow this slide, and you can look at those and make sure you're kind of up to speed. There's also a series of chapter problems, and the chapter problems actually have the answers and stuff following them. I guess I should show them here. So anyway, normally I will stop at this slide, but for this one, of course, I won't. These are the equations for Chapter 1, which I figure are kind of important. And it's equations and concepts, by the way, so I put like significant figures there. That's not really an equation, but you get the idea. Mass percentages. There's the 5 metric prefixes, which are important, stuff like that. And then also at the end, there will be some questions, and these are just some questions with answers, and I encourage you to look through these, try them yourself. And so try these problems. The answers are right here, and so you can kind of check yourself, make sure that you're good to go. But all these ways will help you get ready for Chapter 1 and master the concepts. You can also absolutely email me anytime. I'm more than happy to help. Thank you again for spending time with me here in Chapter 1. Good luck with your studying.